we've established what a vector is, a geometric shift in space tracked cleanly by three perpendicular component numbers. We've added them, subtracted them, and scaled them. But here's the foundational question we haven't answered yet. How long is it? That simple question, how to find the vector's literal magnitude, is far richer than it looks. The answer bridges elementary geometry directly into modern 3D applications. Let's start in 2 dimensions and work our way up. You've seen the Pythagorean theorem. A right angled triangle with legs x and y has a hypotenuse of the square root of x² plus y², making the hypotenuse 5. Now, what actually is a 2D vector? It's a spatial displacement, a movement of x units horizontally followed by y units vertically. Those 2 components are structurally the exact legs of a right-angled triangle. The vector is the hypotenuse. The components are the legs. The magnitude is simply the physical length of that hypotenuse always. In 2 dimensions, finding this magnitude is just classic Pythagoras theorem. So what happens when we step up into 3 dimensions? Our vector now has 3 spatial components. To track its length, we need to employ the Pythagoras theorem twice. First, we apply the theorem to the x and y components resting on the floor. That gives us this flat diagonal distance, the direct route across the floor of the space. Now we apply the Pythagoras a second time standing upright. One leg is that brand new floor diagonal. The other leg is the vertical z component. The final hypotenuse is our full 3D vector. And that is exactly where the 3D distance formula comes from. It isn't an arbitrary rule handed down from above. It's just Pythagoras applied twice. Once across the floor, then straight up through the heights. Here is a subtle realization that trips people up when things get advanced. When we write a vector as a set of numbers, like 3, 2, 5, those specific values depend entirely on the grid system we choose to overlay on the world. Different axes yield completely different numbers. But the vector itself, the actual physical arrow pointing through space, doesn't change at all. The arrow is fixed. The coordinates are arbitrary, and look at the length readout. It hasn't budged either. Magnitude is an intrinsic property of the vector, not the coordinate system. It is the real physical length of the displacement. It doesn't care how you decide to label your axis. This is vital in physics, computer graphics, or machine learning. Your coordinate system is almost always an arbitrary choice you made, but the actual distance between real things are absolute. The magnitude is the ground truth. Everything else is just like bookkeeping. In many applications, you don't care how long a vector is. You only want to know exactly which way it's pointing. Is it pointing up, left, off into a corner? You want pure direction, completely isolated from scale. And to get that, we use unit vectors. A unit vector is simply any vector with a magnitude of exactly 1. It represents pure direction, cleanly stripped of its length. See, every possible direction in 3D space corresponds to exactly 1 coordinate on a sphere of radius 1. That is the unit sphere, and every unit vector is simply a radius of that sphere. The 3 most fundamental unit vectors you will encounter are I hat, j hat, and k hat, the unit directions pointing down the x, y, and z axis. Every 3-dimensional coordinate system is built out of this primary triad. So, how do you take an arbitrary vector of any random length and convert it into a clean unit vector pointing in that exact same direction? You divide it by its own magnitude. That process is called normalization. The hat symbol, written as this, explicitly denotes a unit vector. The mechanical rule is simple. Take the original vector and divide every single individual component by the total magnitude. So using our vector 3, 2, 5, divide each piece by the square root of 38. You get roughly 0.49 along the x-axis, 0.32 along the y-axis, and 0.81 along the z-axis. It points along the exact same path, but its length has been scaled perfectly to 1. Think of normalization as an extraction procedure. You are pulling the pure direction out of the vector and separating it from its scale. The direction now lives in the unit vector. The original size lives in the scalar you divided by. Let's look at the single most common real-world application of magnitude. Finding the exact straight line distance between 2 points in space. We already know from our work with vector subtraction that subtracting one position from another gives you the displacement vector pointing from the first to the second. Therefore, the distance between them is just the magnitude of that difference vector. We take the magnitude of that displacement, square root of 9 plus 16 plus 25, which gives us the square root of 50. Those 2 points sit exactly 7.07 units apart. This is the classic 3D distance formula you've seen in textbooks. But now you can see what it actually is. It's just Pythagoras applied twice to the components of a difference vector. Every time you've used a distance formula, you are secretly computing a vector magnitude. Let's lock this down with 2 practical examples. First, the critical difference between velocity and speed. Velocity is a full vector. It tracks both the exact direction you are heading and your rate of movement. Speed is simply the scalar magnitude of that velocity vector. If a vehicle moves at 60 units along x-axis and 30 units along z-axis, its actual speed is about 67 units. The total diagonal path is longer than either component leg on its own. Second anchor, 3D graphics rendering. Every single surface polygon inside a modern video game engine possesses a surface normal, which is a vector pointing perfectly perpendicular to the surface that tells the engine which way that face is looking. To compute how light reflects off that surface, the game engine needs both the surface direction and the light direction normalized as pure unit vectors. You cannot even begin to calculate lighting or shadows without vector magnitude and normalization. It runs billions of times a second on your GPU. Let's step into the lab to verify this live. We'll examine 3 distinct things. Here is our vector from the first episode, vector 3, 2, 5. The system immediately computes its geometric length using our double Pythagoras math, confirming the value exactly 6.16 units long. Watch what happens when we hit normalize. The arrow scales down perfectly to a length of exactly 1, giving us the pure directional unit vector 0.49, 0.32, 0.81. Same direction, clean scale. Finally, we drop a secondary point into space. See how we calculate the difference vector between them and evaluate its magnitude, delivering the precise distance instantly without needing a physical ruler. 3 raw numbers, 1 elegant formula. Everything else is pure geometry. 3 raw numbers, 1 elegant formula. Everything else is pure geometry. Magnitude is the absolute ruler of vector spaces. It translates abstract spatial directions into concrete, measurable numbers. Normalization is a specialized lens that lets us analyze direction without being distracted by scale. In our next episode, we are going to dive deep into the dot product. It brings together everything we've built so far, components, vectors, and magnitude, to answer one core question. How much are 2 different vectors pointing in the same direction? That single concept unlocks physics, advanced lighting, and modern AI. Thank you for staying with me in this video. Don't forget to like and subscribe. I'll see you in the next one.